I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on skywave propagation. So, skywave propagation refers to the phenomenon where radio waves are transmitted from the Earth's surface into the ionosphere and then reflected or refracted back to the Earth. This allows radio signals to travel beyond the line of sight and cover longer distances even around the curvature of the Earth. Skywave propagation is especially important for medium to long range communication and plays a significant role in amateur radio, short wave broadcasting, and long distance military communications. Skywave propagation, the basic concept is it occurs when radio waves, typically in the high frequency band, that is 3 to 30 megahertz, are transmitted upward into the ionosphere. The ionosphere is a layer of Earth's atmosphere that is ionized by solar radiation, and the ionized layer can reflect or refract radio waves back toward the Earth's surface, allowing for long range communication. And the transmission mechanism is a transmitter sends out a radio wave that initially travels upward in a straight line. Once the wave reaches the ionosphere, it encounters different layers of ionized particles. So, depending upon the frequency of the radio wave and state of the ionosphere, the wave is either reflected or refracted back towards the Earth's surface. The radio wave then travels across the Earth's surface and is received by a receiver located at a distance. Ionosphere consists of several layers of ionized particles that reflect or refract radio waves. The key layers of the ionosphere are the D layer, 60 to 90 km above Earth's surface. This layer absorbs lower frequency radio waves below 2 MHz during daytime, causing them to be attenuated or absorbed. It has a strong effect on the propagation of lower high frequency signals. And the E layer is 90 to 120 km above the Earth's surface. This layer reflects radio waves in the lower high frequency band 2 to 5 MHz. During the day, it plays a significant role in reflecting signals over medium range distances. It is weaker at night but still can influence signals. And F1, F2 layers, that is from 120 to 500 km above Earth's surface, and these are the most important layers for high frequency skywave propagation. The F1 layer is weaker during the day, while the F2 layer becomes more important at night. And the F2 layer reflects high frequency signals above 10 MHz, which allows them to travel long distances, that is thousands of kilometers. The strength of ionosphere and its ability to reflect radio waves is influenced by the time of the day, solar activity, and season. And how skywave propagation works is by the phenomena reflection and refraction. And there are several factors influence the successful transmission and reception of radio waves. And the reflection occurs when radio waves hit ionosphere at critical angle and bounce back towards the Earth's surface. Refraction occurs when radio waves pass through the ionosphere, bending according to the ionosphere's electron density. The angle at which the radio waves hits the ionosphere, called the incident angle, which determines whether it will be reflected or refracted, and the distance it can travel before returning to Earth. And the skip distance, when the radio wave is reflected back to Earth after being refracted by the ionosphere, there is specific range at which the wave is likely to return. This distance known as skip distance. The skip distance depends on the frequency of the radio waves, the angle of incidence of the ionosphere, the ionization level of the ionosphere at that time. Low frequency signals below 10 MHz have longer skip distances and can travel over great distances, especially at night when the ionosphere is more ionized. And when compared to low frequency signals, high frequency signals which are above 10 MHz may have shorter skip distances, but they can support multiple hops to reach over long distances. And the critical frequency is another important term in ionospheric or skywave propagation, which is the highest frequency that can be reflected by the ionosphere back to the earth. If the frequency of the radio wave exceeds the critical frequency, the wave will pass through the ionosphere and continue into space. The critical frequency depends on the electron density in the ionosphere, which changes with time of day, solar activity, and geographic location. And skip zones of multi-hop propagation is a skip zone where the radio signals can be received because the waves are reflected away from the earth, and it occurs between the transmitter and the first reflection point in skywave propagation. Beyond skip zone, the signal can be received due to the reflection from the ionosphere. And next is multi-hop propagation. In some cases, a signal can undergo multiple reflections, hopping from one ionosphere layer to another before reaching the receiver. Multi-hop propagation allows for very long-range communications with signals traveling thousands of kilometers. Time of the day, daytime. During daytime, the ionosphere is more ionized due to solar radiation, which enhances the ability of the ionosphere to reflect radio waves. At night time, the ionization of the ionosphere decreases, especially in the E and F1 layers, allowing for long range communication. And the frequency of the signals is also another factor affecting skywave propagation. And atmospheric conditions make another impact, and where like weather and geographical location influence ionospheric conditions, which in turn affect sky wave propagation. And applications of skywave propagation, they are very useful in shortwave radio broadcasting, military communications, maritime and aeronautical communication, emergency communication systems. Now the assessment question. Skywave propagation reflects the frequencies. We know the answer is 2 to 30 megahertz. At what distance the skywave propagation is present from the earth surface is 50 to 400 kilometer. Thank you.